in this figure, each of the capacitor has a capacitance of 4 microfarad, and the potential difference between the points A and B is given to be 28 volts. Your task is to calculate the charge Q on each capacitor and the potential difference V across each of these capacitor. Now, I want you to look closely into the setup. You have a capacitor C1, C2, C3, and C4, and they are connected in a network such that C1 and C2 are connected in series, while C1, C2, and C3 is in parallel. And then the entire thing, C1, C2, C3, is connected in series to C4. Now, the approach that I will be teaching you to solve this problem will be very easy. It is based on finding the CEQ, or the equivalent capacitance. Let's start by realizing or simplifying the network, and you should realize that C1 and C2 is actually connected in series. So if that is the case, then I'm simply going to simplify my network by rewriting my capacitor network into like this. So notice that what happens to C1 and C2 is now reduced into a 1 capacitor with a capacitance equal to C12, and C3 is still here, and C4. So basically, the boxed capacitors is simply reduced to C12. Now in this case, we can recall from our class that if I'm looking for the equivalent capacitors for capacitance in series, I have these equations, so that will just be 1 over C equivalent of 1 over C1 plus C2 plus C to the n, depending on the number of capacitors. So that means to say, in this context, my equivalent capacitance is just C12, and that will just be the sum of 1 over capacitor 1 plus 1 over the capacitor 2. Now, since the capacitance are actually the same, actually I mistype here, this should be -6 farad. So that will just be 1 over 4 microfarad plus 1 over 4 microfarad. So when you calculate that in your calculator, you get C12 to be 2 times 10 to the -6 farad, or 2 microfarad. It means to say that in this simplified version, this is basically the same. It's just that the C12 here should have a value of 2 times 10 to the -6 farad. Okay, now we are not yet done with simplifying. We can simplify this further. So from this network, notice that the one in dotted squares is actually connected in parallel. Now I can further simplify that one to look like this one. So what happens now is I have a new capacitor with an equivalent of capacitance of C123. And this is now the equivalence of these two capacitor in parallel. That is simplified, and C4, it remains as is. So in this case, I now have to recall that the equivalent capacitance for a parallel network, I'm referring to C12 and C3 here, will simply be the sum of the individual capacitance of the capacitor. So in this problem, the C equivalent will just be C123, this one, and that will just be the sum of the capacitor 1, 2 plus the capacitor 3. Now substituting the values, that's 2 microfarad plus 4 microfarad, you get that C123 is just 6 microfarad. Now, this is getting simpler and simpler, but we can further simplify this one. So this capacitor network can be further simplified to look like this one. You combine the capacitor 1, 2, 3 and capacitor 4, and notice that this is actually again connected in series. So if that is connected in series, this will just become a network like this one, C1234. We only have one capacitance now. But since the C123 and capacitor 4 are connected in series, we get the equivalent capacitance, in this case C1234, to be just the sum of the individual capacitance. So in this case, that will be the 1 over C of 123 plus 1 over the capacitor 4. So it's a simple mathematics. So you substitute the values and you end up with 2.4 times 10 to the negative 6 farad. Okay. Now the next step is to solve for the charges Q, voltage V, and this is actually my term. I say you can solve this in retrograde manner because we're going to solve it by reverting until we get the original network. So in this case, I start from the network of the simplest capacitor that I have distilled from all of the steps. Diba? It looked like this one. So from this, I have to solve for the total charge Q. In this case, that will be the Q subscript 1, 2, 3, 4. Now recall from your definition of capacitance to be just the charge Q per voltage. So you get that the capacitance of the capacitor 1, 2, 3, 4 will just be charge of 1, 2, 3, 4 over the voltage at 1, 2, 3, 4. Now I will be solving for Q, so that means to say I have to multiply my capacitance and voltage. Now in this problem, the capacitance 1, 2, 3, 4 is something that we have solved earlier. This is the equivalent capacitance of the entire capacitor network, and that is just 2.4 microfarad. And then the potential difference across the entire network is just 28 volts. It's given in the problem. So this gives me that the Q1234 will just be 6.72 times 10 to the negative 5 coulombs, or 67.2 microcoulomb. Now, why this is significant? Because notice that the combination of the network capacitor network C1234 is actually a series network of two capacitors C123 and C4. Now this is very significant because you have to understand that once your capacitors are in a series connection, that means to say that the charges must also be the same for each of these capacitor. So that means to say that the charge Q1234 that I have solved will be the same charge for the capacitor 1, 2, 3 and capacitor 4. So I've written here that Q1234 will simply be equal to Q123 and Q4 with a magnitude of 6.72 times 10 to the negative 5 coulombs. Now, So at this point, we can now solve for the potential at 4. So the voltage at the capacitor 4. Okay, by definition, again, your capacitance is just the charge per voltage. And when we redo this equation in the context of the capacitor 4, the capacitance of capacitor 4 is simply Q4 over V4. And rewriting this, we have V4, potential at 4 is just equal to the charge at 4 over C4. Now remember that the charge at 4 is the same with Q1234 because they are connected in series. So you substitute 6.72 times 10 to the negative 5 coulomb in place for Q4. And then the capacitance at 4 is 4 times 10 to the negative 6 farad. So you get that the potential at 4 is 16.8 volts. Now for the potential at capacitance 1, 2, 3, that will be Q over V, still the same definition. We're working with definition here. So we get that the voltage will at 1, 2, 3, voltage 1, 2, 3, referring to this capacitor 1, 2, 3 over here, will simply be the charge at 1, 2, 3 divided by the capacitance at 1, 2, 3. Now notice that we still use the same value, 6.72 times 10 to the negative 5 coulombs. This is the same with the charge at Q4 because again, as I've said, it is because of the fact that these are connected in series. So that means to say whatever charge that you have over here at Q1, 2, 3, 4, it must be the same charge that is stored on these two capacitors since they are in a series network. Alright, so I'm just trying to explain again because that's basically the entire thing that you have to note in this problem. So in this case, when you do your calculation, you get that the voltage or electric potential at the capacitor 1, 2, 3 is 11.2 volts. And notice when you add this one, you end up with 28. which is the given voltage. So this is a good sign that you're getting the correct answers. Notice, however, we're working back that this illustration that you're seeing here, we have now solved for V123 rather, and V4. But if you think about it, this capacitor 123 is actually a parallel network of two capacitors, which are C12 and C3, like this one. So what this implies is that the voltage must be constant across the capacitors C12 and C3. Okay, so that means to say that previously your C123 has a voltage of V123. We have solved this earlier, which is equivalent to 11.2 volts. And since this combination is actually just a parallel network of C12 and C3, this means that the voltage at 1,2 for capacitor 1,2 and the voltage at capacitor 3 or V3 should be the same value at 11.2. So that's the implication of that one. So that means to say then that we can solve for the charge at 1,2. So solving for charge at 1,2, we will use the definition of capacitance as charge per voltage. So you just have to rewrite that one. Q12 will be the capacitance 1,2 times the voltage at 1,2. And simply substitute the values, so you get that the charge stored at capacitor 1,2 is 2.24 times 10 to the negative 5 coulombs, or 22.4 microfarad. Now, in the same manner, you can solve for the charge stored at Q3, at capacitor 3. Maybe we use the same equation by definition of capacitance. So that will be Q3 times the capacitor 3 multiplied, the capacitance 3 multiplied by the potential at 3. And again, notice that the same reason that I have keep on repeating, your voltage 1, 2, 3, if you think about this capacitor over here, is simply a parallel connection of two capacitors. Therefore, whatever voltage that passes through these two capacitors connected in parallel, it has the same value. That is why in this calculation, you should not be surprised that V3 that you're using is the same as before with 11.2 volts, because they are actually connected in parallel. So I keep on repeating myself, sorry. So by Q3, you simply have to calculate that in your calculator. You end up with 4.48 times 10 to the negative 5 coulombs. So this is the charge that is stored on your capacitor 3. And further looking or working backwards, we are now dealing, previously we deal with this one, C123, we break that one into C12 and C3. So now we will be breaking further apart your C12 and realize that C12 is simply a series network of two capacitors, which are C1 and C2. So the same application that we had earlier, this means to say that the charge 2 must be constant across this capacitor. That means that the charge at capacitor 1 and capacitor 2 must be the same. And in connection, that should be equal to the charge at the 1, 2 here for the combined capacitors. So the Q12, the charge at 1, 2, should be equal to the charge at capacitor 1 or Q1, and the charge at capacitor 2 or Q2, which has this value which we have solved earlier, 2.24 times 10 to the negative 5 coulombs. Now, since we have the value of charge, by using the definition of capacitance, we can solve for the potential at point 1, at capacitor 1. So we have to rewrite our equation. So we have V1 will just be the charge at 1 over the capacitance at 1. So we simply substitute the values, and plugging in the values in your calculator, you end up with V1 to be 5.6 volts. Now at this point, we do the same thing about your capacitor 2 and solve for the voltage across that capacitor. So that would be V2 is equal to Q2 over C2. Substitute the values, so you end up still with the same value, 5.6 volts. Alright. So in summary, we have solved everything now. for the capacitor 1, we get that the charge stored is 2.24 times 10 to the negative 5 coulombs. The potential difference across that capacitor is 5.6 volts. For capacitor 2, it's 2.24 times 10 to the negative 5 coulombs. The potential difference across this capacitor is 5.6 volts. For capacitor 3, we have solved that the potential difference across this is 11.2 volts. And the charge stored in this case is 4.48 times 10 to the negative 5 coulombs. And for capacitor 4, we get that the charge stored there is 6.72 times 10 to the negative 5 coulombs, and the potential difference at this point is 16.8 volts. So that's how you approach this problem. Again, I'm going to summarize everything. First, from your given capacitor, you have to simplify it further. So just like this. And you solve for the equivalent capacitance. And again, simplify it further until you get the simplest form, and you solve for the equivalent capacitance until you get this one. So once you get here, you get the equivalent capacitance of the entire network, and you work backwards. So this is where I said that you work in retrograde. So from here, you solve for Q, and you can solve for the charge there. And then once you know that one, you realize that this connection is just series. So what are the implications of that? And again, after working with this, you break down further the capacitor 1, 2, 3. So that's basically it, like this. So you break down further 1, 2, 3 to be the capacitor 1 and 2. And you think if it's parallel, then the voltage will be the same. If it's series, the charges would be the same. So further break down your capacitor 1, 2. Okay, you rest with series, so the charges must be constant. So basically, that's the entire gist of solving problems involving capacitor networks.